two co-authors. Dr. Daniel Spicer, Ph.D. He's been a research professor of physics at Drexel University in Philadelphia since 2007 and is an emeritus scientist at NASA's Goddard Space Flight Center since his retirement. Since his retirement from NASA, Dr. Spicer has worked together with Bob Siefker, while part of Dr. John Jackson's Shroud group, to produce a critical summary of what is known about the Shroud, and that can be found at www.shroudofturin.com, not to be confused with shroud.com. Shroud, that is shroudofturin.com. His co-author is Edward Toton. He's president of his own company, and they provide program assurance and technical assessments for government and industrial organizations in the areas of electromagnetic theory, fluid mechanics and shock waves, risk assessment methodologies, and other areas. He has approximately 100 publications and journals in government publications. Dr. Spicer.
Basically about what we view as the image formation mechanism for the shroud. And will be basically what we call, first, the two of us, a 3D Xerox machine. And we'll show you how that all works. First slide here. Now, there are two key measurements we made by the STIRP team, and that is the image exists on the surface. And when I say, you notice I put in parentheses S or question mark, because it's not clear to me yet whether there really is more than one image on, at least on the ventral side of the cloth. There's an image on either side of that cloth surface. But this mechanism will produce two images. If it's one of which will be very weak, as Fonte's paper indicated. The second point is that there's no image or discolorization between the two surfaces of the one, well, between the two sides of one surface. Just everything is right at that surface. It's those threads are the only things that seem to be discolored. And the final thing is that the image density on the cloth is directly proportional to the distance from which the body is covered. Now, the third thing indicates to me, and it's pointed out by John Jackson to me, that indicates it's an effector field. The first two things indicate to Toton and I that it's an electric field. This is characteristic behavior of a dielectric. And, it's very common, and you'll see how that all works shortly. The final point that I make is the image does not fluoresce according to the STIRP results. That we don't try to explain, except for, we can explain it, but it's kind of a maybe answer, because we think it really is going to tell us what the oxidation mechanism really is, because if the rest of the cloth fluoresces, and the image doesn't, there's something, the image process that made the image has changed the properties of the cloth. So that you may be able to reverse the logic and figure out what actually is causing the oxidation by looking at the fluorescence issue, by identifying what's causing the fluorescence. Okay, what we do, we make one assumption, or a hypothesis, and that is there's a vertical electric field within the tomb. And the mechanism for the generation of that electric field right now we're not going to mention. We're just going to go forward and see what the consequences of that electric field will be. The strength of the field is also unknown, but it's well below the air breakdown value of about 3 megavolts per meter, which is required to the model, I think it's called the current discharge model. So that's a very large electric field, and we don't feel that's necessary to achieve the image. In fact, that's so large it wouldn't give you an image, it would charcoaling of the shroud. So that's almost like a lightning bolt hitting it. And it's probably, the electric field is probably equal to or greater than the electric field we find in the atmosphere of the Earth. Right now, as you're standing there, there's at least a 200 to 300 volt voltage drop per meter in the atmosphere. So it's there all the time, you just don't notice it doesn't have much current. Now, there have been about 9 people who have proposed electric fields. Unfortunately, we couldn't get all the references, so I'd like to acknowledge it. The only really 2 that we could get our hands on were, I'm sorry, these 2 by Delisa, I guess it is, and Giulio Fonte. But they never discussed some of the physics I'm going to discuss now. I don't know why, but they don't. Because it has a major impact on how the image would be made in the electric field. I'm also going to discuss some what I call principal facts. It's basic physics, first-year physics in college, or if you went to a good school in high school, you probably also ran into it. There's nothing I'm going to talk about that's quantum mechanics or anything of that nature. It's just stuff you would find in any textbook that you would get in a first-year course. The first point is that the human body is an excellent conductor for low-frequency electric fields. That's not a disputed fact. And that's mainly because your body is 70% water reliance throughout it. The shroud cloth, however, is an excellent dielectric, or sometimes referred to it as an insulator. And in fact, early capacitors, which is a form of storing electrical energy, were made with linen back in the 1900s, 19th century, I would say, and early 20th century. In addition, another concept we're going to introduce is polar molecule leadership. I haven't seen in any discussions. In urea, ammonia, and aloe, to give you an example, are excellent polar molecules. All molecules have to, I don't know, can't think of one that's not a polar molecule. Almost all polar molecules are polar in some form or other. They're either very, very small polarity or very large. The biggest one we found is, in fact, urea, which surprised us. Which you'd find in body sweat. Any boy who's on a football team or baseball team out in the field play, when he comes home, his mother's going to have a fit trying to get rid of the yellow stains in his armpit, which is where that comes from. Armpit of his t-shirt. Now, what I'm going to show here is we start with an example of a capacitor where we put a material which is a dielectric. But we have not turned on any currents or voltages or anything like that. We just want to show you that the polar molecules that are inside that dielectric will be randomly oriented. And the moment we turn on the power, we will get a polar molecule become oriented. But the key thing here to remember here is I have a capacitor with an electric field running from this point to that point. And you have positive charge on that side, negative charge on that side. And you'll notice that here you have negative charge here, and negative and positive charge here. This is characteristic of a dielectric. You turn on electric field, one side that's closest to that power, that electric field will give you one sign, which is the opposite of what the electric field is actually providing. And then when you go to the other side of the dielectric, you'll find the opposite sign. And the other point is that the surface charge density, which appears on opposite surfaces of a dielectric cloth, will be proportional to the electric field perpendicular to the cloth. Now, again, this is anything, this is standard physics. There's nothing you're going to find here that you should concern yourself with in terms of it's valid, solid. Nobody's going to argue with it. No physicist is going to argue with anything that's safe in this particular view. Except for we're going to assume a vertically aligned electric field. And it's going to be uniform in space. It's going to be quasi-static. That means it can vary a little bit in time, but pretty much slowly varying in time. Its direction at the moment is indeterminate. It can be in either direction, actually, for our purposes. Its origin is unknown, but the potential sources, which I'll discuss a little bit later in more detail, the ambient electric field of Earth, the thunderstorm generated ambient electric field, radon charge separation in the tomb. We could have radon was there, and piezoelectric fields in rock, which occur. You heard about that this morning to some degree. All right. The first thing you want to understand about a conducting body. Now, the conducting body in this picture is the body, Christ's body in the shroud. And it's in a conductor. There is no electric field is allowed within the conductor. The second thing is the long-term behavior of a conductor. If you do charge up a conductor, it will distribute itself very quickly around the surface of the conductor in such a way as to generate an electric field which is perfectly normal to that face or that boundary, or in this case, surface. And the electric field and the charge density distribution will be maximum where the surface has the greatest is greatest in convectivity. I always say it wrong. But anyway, it basically says things like your nose, if you get charge on your nose, your fingers, your eyebrows, things like that on the image that we're going to describe will have the greatest density in charge density as well as electric field. So the charge distribution depends on the geometry of the conductor. In this case, again, it would be the human body. And the charge distribution then contains geometrical information about the properties of the conductor. Now, this is just a simple 2D calculation. We use a model for the body as a cylinder. And we can solve the relevant Maxwell equation, which is only one actually, just of the four. The one we needed to solve was just the divergence of the electric field is equal to 4 pi times the charge density. But it's a pretty straightforward solution. And this basically shows that the distribution of charge throughout over the surface of this cylinder, this cylinder here, which is a circle, and everything's uniform in the z direction, which is normal to the sheet. But the charge density will be distributed in such a way, most of the charge will be right up here, and a little down here, the negative. The opposite charge will be down here, and there won't be any charge in this plane here. And you can see that in the expression you get for the charge density, surface charge density, to be precise. So again, the surface charge density contains the essential vertical displacement information also, as you can see in this equation, for the charge density here. Now, what we've done here is we've basically taken a cutaway of the human skull and with the nose in it. We've taken a little box here and we've blown it up. And this would be the cloth shroud laying over, which would be right here. Just take a little cutaway. And you'll notice we're assuming the electric field is vertically downward in this particular picture. And what we're going to find is when you look at the distribution of charge, the top of this cloth will be a negative, and just below it will be positive. And what will happen is in regions where, such as your nose, you will get a buildup in charge, which is much greater than other places where the surface doesn't have as much it's not as convex. Now we're going to look at that a little bit more in detail. Now, the next thing we're going to do is we're going to allow a diffusion of something which is an impurity on the body, the surface of the body. That impurity in this case was, we chose to be urea, because that was a simple one. We could find information about its polarity in the literature. And what we find is, again, we have a vertical electric field pointed downward, and what will happen in the body is down here. So the urea will diffuse upward. Now, previously, you will find in most of the literature, people discarded urea as a possible source for forming the image. And the reason for that was it's a diffusion process. It's not going to give you a sharp image, as you see in the shroud. The difference, though, is because the charge density will be greatest in those regions where you want it to have a lot of resolution, which is because of the way a charge distributes itself on the dielectric when it's enclosing a conductor. You're going to get a lot of urea in those regions and hardly any urea in other places. So you have areas where there'll be a good, sharp, detailed image, and other places where there's hardly any image. And what will happen is these are the molecules, the chemical form of it, and they'll be deposited along here. But some of these urea molecules will diffuse through that cloth. They, in principle, could attach themselves at the top surface and give you a weak image. We don't think it'd be much of an image because we don't see how we get all these things through. And not only that, the urea itself, in this particular case, will have a different polarity and won't attach itself so well at the top. We exaggerate the charge here in terms of depth. It's only one layer, one thread, or a fiber thick. So it's not very deep. And if you look at a dielectric on a microscope, you'll see how those threads will actually build up in charge, and it's only on those threads at the very top. So what these electric fields do is basically concentrate the impurity to the points along the places you want it to concentrate, and it freezes the information on the body onto the dielectric. Now, other characteristics which are naturally explained by this mechanism is that there are going to be body there'll be regions where there is no visible contact. For example, right where you're just between your nose and here, you're not contacting if it's just laying a cloth over your face. So you're still going to get an image on there. Secondly, like Flante likes to use the word doubly superficial. You can get that with on the top, the ventral side of the cloth. You'll get two images. One will be a good image, and the other one will be a very weak image. And in the dorsal side, you only get a single image, and the reason for that is if the body is either laying on a stone or on the floor, there's no way for any of the impurities to diffuse out of it to get to form that third image. There won't be any image on the top or the sides. That's simply a result of the fact that the electric field is normal to that to the side and the head. Therefore, there won't be any charge separation. Again, this is simply a result of the fact that the charge only lies on top of the surface, and therefore the impurities also. Now, we looked at various possibilities for the sources of the vertical electric field. I mentioned earlier that the atmospheric electric field is typically anywhere from 100 to 200. I've now recently found some people say it's as high as 300 volts per meter. And if you want to read about that, you can find it in Feynman's lectures, volume 2, on the lecture. It's a kind of bedtime reading for physicists, but you will, it's right in there, and he discusses how it works and how it comes about. But it's everywhere. It's here in this room. You just don't feel it. Now, interestingly enough, during a thunderstorm, they measure anywhere from 1 to 10 kilovolt in a thunderstorm per meter for average electric field. A radon in the tomb. Now, I should point out, these two are downward pointing electric fields. In the tomb, we would get a upward pointing electric field because the radon is heavier than air and therefore, much denser, so it will lie at the bottom of the tomb, and the alpha particles, which that are decaying, can't go any further than about 4 or 5 centimeters, and therefore you'll get a layer of charge, positive charge down there, where the electrons, which are beta rays, as they sometimes call them, will be coming out of that region. They have a much higher mean-free path. Therefore, the electrons can get to the roof of the tomb, and therefore you get an electric field set up in that tomb. Now, the value of that electric field is, we don't know, but we do know that from looking in the literature and I've talked to a number of friends of mine at the University of Tel Aviv who tell me that they find electric values as high as 200,000 becquerels, which is a measure of the how radioactive the radon is. And geologists tell me that below, in regions where there's lots of earthquakes, you can get pockets of radon, which can then bleed up into a region above that pocket. And if you have a tomb there, obviously you could leak right into it. And you could feed this for some time. And of course, then there's a piezoelectric field, which the direction could be anything, and the magnitude could be anything too. We have no feel for that at the moment because we haven't really researched it. And that's basically just another term in Ohm's law. So there's a variety of possibilities for getting that term. We're looking at those. So these are the 4 probable ones, but we feel probably the first and second one are most likely. And which one it would be would depend on how fast the image is oxidized. That is, how fast that impurity will oxidize the thread. Now, I mentioned this earlier. Why doesn't the image fluoresce? Well, we feel that we're going to turn the question around, which is turning on its head, basically. We believe the oxidation mechanism, whatever it is causing the fibers to yellow, is somehow changes the emission state, the allowed emission states that allow things to fluoresce. So if we could determine then what is in fact causing the fluorescence, we think it's probably fluorite. And I understand Alan Adler thought it was something called pectin residues that were left over from the retting. I don't know which one it is. That can be done by an experiment. But whatever it is, once you know what it is, you can use that information to react, to get that chemical to react with the impurity you think is working, and that will then test it to see if it fluoresces. So you can at least do, by a process of elimination, reduce the number of possible things that are causing the oxidation to something that's reasonable and workable. So what we would suggest we do here, as far as actually demonstrating this, is we need some scale tests. We think we can do a simple test in a laboratory without any too much difficulty. Looking at the image formation. We're also going to do, we've already started on the second one, which is a mathematical modeling, and we're going to do it in a much more rigorous way than the cylinder. Let me see if I can put this mouse over here. can't see it when I'm standing up that high. Yeah. We've got a grid we've generated for a body with the hands crossed and the nose and everything. It's too dense where the head is. And we're just going to solve the appropriate Maxwell's equations, which again are just the one Laplace equation for the electric field and therefore the charge density. And once we have that, then we can wrap the shroud with a model. That'll change the boundary conditions, and then we'll have some equations which will describe the diffusion process, and we can do the whole calculation. Shouldn't be that difficult to do. It's just a question of time. Let's see. Okay. We need to get some time constants from people on, if there's any out there, for body relaxation following rigor mortis. We call it versus rigor mortis versus theta rigor mortis, whether it's fast or slow. Because if we're not sure when the image was formed, so you got to put some limits on how fast this mechanism can work. And we know that when a body comes out of rigor mortis, it can move. So the image, so that's kind of an upper limit on the time. We don't know what those numbers are. A friend of mine who was was a physician who was also a medic in the Vietnam War tells me that these bodies, a wounded man who dies in battle, he's under extreme situation, just almost like you would have with crucifixion. He will go through rigor mortis rather quickly, and he said it's like anywhere from 9 to 10 hours. So you don't have 36 hours to make this image. You have like 9 to 10 hours. And where were we with the last one? Then we're going to look at the search for mechanisms for field generation. I wanted to say one more thing about the image and why it's unique. When I first looked at this question, because I heard this question asked a lot, well, if you have a mechanism, how come I see other images like this and other burial cloths? I think the thing I found most fascinating was the fact that this was an exceptional burial. I found in the historical write-ups that those people have put together that except in times of war and revolts, the burial of an executed prisoner was in conformity with both Roman usage and Jewish usage or Jewish law. The bodies of the executed were thrown into pits, just to basically decay. But the man in the shroud received what I would call a very honorable burial. It is in a truly exceptional manner. That cloth is an exceptional high quality cloth, or precious cloth, and they cover them with various things like aloes and possibly myrrh, other things of that nature. But the second thing is that body was unwashed. And I think that's really important. One of the reasons we see this image, if anything I've just told you is correct, and it's consistent with Jewish rites. Now, and if I take just those two things, you can see right away you have three sets of people here, basically. The people who were executed, who were they weren't washed, and they were literally thrown into the pit. And the second set of people, you would have people who died normally, who were washed, and they were also put in a tomb, and they were covered with a cloth. But the third type is the type that that went through the same procedures as the first set, but were buried in a tomb, but weren't washed. And so if you look at just overlapping sets, you see basically you have one person out of that whole Jewish population. Now that's only applicable to the Jewish population, but you can go through the same kind of argument. If you're familiar with the Drake equation for predicting livable planets, it's the same kind of mathematics. The problem is getting those parameters. The astrophysicists had problems with figuring out those parameters. We have the same problem because we couldn't come up with any we felt comfortable with those numbers. But I think it's those things, it's a combination of the first two things and possibly the existence of of storms or earthquakes, because somehow we have to get that electric field. Let's see what else is there. And so our conclusion is you shouldn't see any other images for those reasons. Let's see, I think that's about it. Oh, we do predict, though, which is important for a good theory. If a theory doesn't predict something, it's useless. How do you test it? Except for it's consistent. There's lots of theories that are consistent, but they're not right. We predict that there will be lateral distortion of the image. When you go from the center of the body toward the edge of the body, you should see distortion. It's not a lot. It's second order. That's only first order correction. And we also predict that the concentrations. We've read a number of papers. We're kind of getting confused by this particular one because we see people saying that these densities on these threads they're binary. They're like they're switching on and switching off. We find that difficult to believe, but it's possible, I guess. But we think it will be continuous densities. In other words, it will be partially, some part of the thread will be partially oxidized and other parts will not be. We need to get from people, if they know it, or chemists who can do these things for us, get some quantified numbers for the dielectric properties of the shroud material. We have to figure out what the dominant chemistry is. I think we all want to do that. We need to get the source and time evolution of any electric field, and whether it's a slow accumulation or a snapshot exposure. It could be very, for all we know. And I've already mentioned the last one, which is that you can get that extra image on the other side if need be. Okay, one. Okay, I think I'm. We got a few minutes yet, so. No. Okay, real quick. So what we do is we start with a quasi-static electric field. I just want to summarize this, and everything else follows from just the assumption of the electric field. The electric field, as I said, it has to be normal to the conducting body. Produces a surface charge in the body that is always directly proportional to the electric field. The electric field polarizes both the dorsal and ventral surfaces of this cloth, as well as a vertically polarized body, polarizing the body. The surface charge lies on the crowns of the outer cloth surface fibers. And the polar molecules, this is the key here, present on this body surface will diffuse from the body cloth to the cloth, where they concentrate at the locations of greatest surface charge density on the cloth. And they will act as the polarizing agents, which will change the color of the surface fibers. We also feel that if there's a sidurium there, it won't make any difference. But we also think it's possible that we can make the image the same way in the sidurium rather. So that's basically the summary. And I just want to acknowledge the help of John Jackson and his team, where I learned a lot of these things. And Barry Schwartz for helping me when I needed a paper or his valuable memory, because he seemed to have encyclopedic memory. And my Bob Siefker, who's helped me quite a bit with the history and the medical stuff, forensics. That's about it.